Hi, I'm John from Atmel, and I'd like to talk a little bit about compiler performance today. The compiler is the single most important element in the toolchain, and it directly correlates to the size of our application and to the performance of our application, and quite often both. Obviously, size matters. If you have an application that's just barely fitting in 32 kilobytes of flash, and it's that one extra byte takes you to a 64 kilobyte, that's a huge increase in expense, and it's completely unnecessary if we can find a way to get our code to fit. Likewise, speed matters. If we're working with a set of application requirements that include user interface, touch response, interactivity, we also have networking response, we have perhaps an underlying control algorithm, all of those deadlines need to be met. And if we can't make that happen in a performant way, we have to upgrade the clock speed of our processor, we have to perhaps use a 32-bit processor. So what I'm here to talk about is the idea that the compiler might in fact give you or buy you time to make those more dramatic changes that would increase the cost of your device. Compiler performance is quite astonishing, and if you haven't spent some time studying what a compiler can do on your behalf, I really encourage you to look at. I've itemized some of the really important features here. It is truly a marvel, as it can go in and find particular pieces of code that can be hoisted out. It can roll out of loops code that was invariant, that's no longer necessary to be part of a loop, so it can reduce the execution time. You can go in and actually do the unrolling of a loop, which means you can actually make the loop operate sequentially as a number of times in order, instead of operating it iteratively with taking the test clause each time. And the fact that it can do all of this examination of the code and produce the necessary code without making changes to the code itself are really quite brilliant. So I think with all due credit to the compiler, we have to also doff the hat to programmers. Human beings still have a role, and specifically in the area of algorithms. And this is an area where, of course, compilers are not going to offer the support. My favorite guiding light, Newton's method, extraordinarily effective. Very short number of iterations getting to the root of an equation. But also Hoare's quick sort is an example where if you're sorting a large amount of data, it's an amazingly elegant algorithm. Compilers are not going to be able to examine code and make those sorts of selections, but you obviously have that obligation, but it would be silly not to look to exploit the compiler for what it does best. Let's work a quick example. If we look at the performance, and specifically around code size, let's take the sign function. A lot of the times in the microcontroller space, we decide not to utilize a floating point unit. That saves us some money, it saves us certainly a lot of silicon real estate, and then it presents us then with a classic challenge. How do we perform a transcendental function like sign? Well, if we look at the option one, lookup table. The problem with the lookup table is depending on the resolution of the particular sign. The example I have in my mind is perhaps a rotary encoder, perhaps it's 18 bits. If I'm going to pull that in, that is an enormous lookup table to go through and figure out the sign values. There's also the CPU implementation. I can use the Taylor expansion, you can see it here, and I can do a fixed point implementation of that. So the difference between those two is about 512 kilobytes. That's a rather substantial difference in approach based on just the algorithms I choose. Here, for those of you who are interested, is the actual fixed point arithmetic implementation. The message I want to send here is this is not easy. I mean, you have to spend some serious time to make sure you're protecting resolution, that you're not losing some decimal places. You can also have an option to go even beyond using the processor at all. You can commit an algorithm like this straight to hardware. Here's the exact same algorithm utilizing 4 18 by 18 bit multipliers. And so in this case, it's taking up now hardware real estate, but no processing flash space whatsoever. Let's work another example, execution time. In execution time, a really very clever implementation is available when you're doing memory copies. Look at the implementation of memcopy, a standard POSIX routine. Here we're just doing the test first and last, and we're moving one block of memory to the next. But the problem with this implementation is we're repeating that test every single time we're making that move. It's crying out to be unrolled, and here is in fact an implementation in ANSI C of unrolling that loop. It's called Duff's device. Incredibly clever. A lot of people looking at this code scratch their heads saying, is that even ANSI C? Sure enough, it is. It's compliant. It's syntactically correct. But look at that construct. We're actually doing a do-while loop into a switch statement, or rather a switch statement into a do-while loop. That's what really allows us to emulate what a compiler does for us, which is unroll that loop. So this is an example where, sure, we could be clever. We could spend a lot of time working on these algorithms. But before you break out that sword, I invite you to start by trying a really good compiler. Kyle is an excellent compiler. It's available through our extension gallery, and if you haven't taken a chance to take it down, work with your code, see if it gives you the kind of performance requirements you need, I really invite you to do so. Thanks.